Dear students, last time we discussed basics of vector fields, scalar fields, and we defined curl. So recall curl of f. It is also denoted by del cross f, where this del is operator given by partial derivative with respect to x into I hat plus partial with respect to y z hat plus partial with respect to z k hat. Okay, and this capital F is from R3 to R. It is differentiable vector field. Now we define divergence of vector field. So, as in last case, we consider F from R3 to R a differentiable vector field. So, divergence of a vector field. Let F from R3 to R be a differentiable. Yeah, it should be from R3 to R3. Be a differentiable vector field given by f of xyz equal to p of xyz into I hat plus q of xyz into z hat plus r of xyz k hat. Okay. The divergence of capital F is a scalar field. Okay, remember that. Gradient of vector field is again a vector. This del cross F is a vector. So here divergence is a scalar field. Is a scalar field defined as so notation is DIV, divergence of F equal to, its definition is del dot F. Okay, so this is dot product of these two vectors. Okay, so it is equal to, so del is, it contains partial derivatives with respect to x. Okay, I hat, z hat, k hat. So we may write this equivalently as components, partial derivative with respect to x, comma with respect to y, and comma with respect to z. Okay, as a vector. So this dot with f. So our f is p comma q comma r. Okay, so this may be written as p q r as a reflet in R3. Okay, so dot P Q R. Now we know how to find dot product of such two vector quantities. That is partial derivative of p with respect to x. Note that this is not a vector, so we don't have multiplication. Instead, this del is an operator, so we take partial derivative of p with respect to x. Okay, it is not a multiplication. Partial p with respect to x plus partial q with respect to y plus partial r with respect to z. Okay, so this is our divergence. Next thing is gradient of a scalar field. Okay, so we consider curl and divergence of vector fields. Now we consider gradient of a scalar field. So we consider scalar field phi let phi from R3 to R be a differentiable scalar field, then the gradient of phi is defined as del phi. Okay, so we also denote it by grad equal to del phi, and del phi is nothing but partial with respect to x, partial derivative of phi with respect to x into I hat plus partial derivative of phi with respect to y z hat plus partial derivative of phi with respect to z k hat, or equivalent it is vector partial phi with respect to x with respect to y and with respect to z. Okay, so these are three important things. Curl, that is given by cross product. Divergence, it is given by dot product. And gradient, it is just operation. Okay, so phi will operate on scalar field phi. Del will operate on scalar field phi. Now we see some properties. One theorem. Let vector field f be given by p into I hat plus q j hat plus r k hat. Note that p, q, r, f, all these are functions of x, y, and z. Be a continuously differentiable vector field continuously differentiable means derivative exists and that derivative is also continuous. In this case, mixed partial derivatives will match. I mean, partial with respect to x with respect to y is same as partial with respect to y with respect to x. On an open convex set S in R3, on an open convex set S in R3. So open set. Means if we consider any point in that set, then we should be able to find an open ball around that point which contains which is contained in that set. Okay, so what is meant by open ball? Open ball is means neighborhood. Okay, so this part is from matrix space. Okay. Convex set means roughly we can say if we consider any 2 points in that set, we should be able to sketch a line between these 2 points, which is totally in that set. Then F equal to gradient of phi for some scalar field phi if and only if we have curl of F equal to 0, 0 means 0 vector. Origin, we can say origin. Okay. That is, okay, here F is gradient of phi. So curl of gradient phi equal to 0. Or you can say del cross del phi equal to 0. Okay. If phi is a scalar field, then we have to prove that del cross del phi is 0. Okay. So proof. So we have del phi equal to partial derivative of phi with respect to x into I hat plus partial with respect to y, z hat plus partial of phi with respect to z, k hat. And therefore, del cross del phi equal to, it is a determinant whose first row is determinant of a matrix whose first row is I hat, z hat, k hat. Second row is components of this del. These are partial derivatives with respect to x, y, and z. And then components of this vector del phi. And these are partial phi with respect to x, with respect to y, and with respect to z. And this determinant equal to I hat into this operator is operating on partial derivative of phi with respect to z. So it will be partial 2 phi by partial y partial z. Okay, that means first we take differentiation with respect to z and then with respect to y, minus same thing partial 2 phi by partial z partial y minus z hat into partial 2 phi by partial x partial z minus partial 2 partial z partial x, and third plus k hat partial 2 phi by partial x partial y minus partial 2 phi by partial y partial x. Now capital F is continuously differentiable, therefore we must be able to write that these two quantities are same. This order doesn't matter whether we are taking partial derivative of phi with respect to z first and then partial derivative with respect to y, or partial derivative with respect to y followed by partial derivative with respect to z. Doesn't matter, both are same. So this will be 0, this will be 0, and similarly this will be 0. So therefore this second order partial derivative is like this, equal to etc. Yes, same here. So therefore what we get? We get 0. Del cross del phi 0. This proves the result. Next. Next result is first thing is trace of Jacobian matrix is divergence of F. So trace of a matrix means sum of diagonal elements. Okay. So trace of Jacobian matrix, and trace of a matrix is sum of diagonal elements. Okay, so if we have this matrix, then addition of all these elements. Okay, so these are diagonal elements. Is okay, so here we are taking Jacobian matrix of capital F. Trace of Jacobian matrix of capital F is divergence of F. Next thing is if Jacobian matrix is symmetric, then curl of F is 0. If the Jacobian matrix of capital F is symmetric. Symmetric matrix means transpose of that matrix is same as itself. Means if we interchange row and column, then we get same matrix. Okay. So if A is say A11, A12, A21, A22, for example, it is 3 by 3 matrix here. Okay, I should write A13, A21, A22, A23, A31, A32, A33. Okay, and here it is meant by A is symmetric means Aij equal to Aj for all Ij. So this means symmetric. A is symmetric. If the Jacobian matrix is symmetric, then the curl of f is 0. Curl f equal to 0. 0 means origin here. It is vector, okay? It is not a number 0. We are not going to discuss the proofs of these results. We solve examples. Okay. Example. Show that the curl and divergence of f given by minus y upon x square plus y square I had plus x upon x square plus y square z hat. Okay, k hat is absent means it is nothing but 0 into k hat. Okay, so curl and divergence of this f is 0. Let us see. So curl of f is del cross f and it is equal to determinant of a matrix whose first row is I hat, z hat, k hat. Then partials with respect to x, y with respect to z, and these components minus y upon x square plus y square, x upon x square plus y square, and 0. So this determinant becomes I hat into partial derivative of this function with respect to x. So it is, we need to use product rule or quotient rule here. It is simply 2 times xy upon x square plus y square bracket square. Okay, so we are differentiating with respect to x, so denominator x square plus y square let me write once again. It is denominator x square plus y square into derivative of numerator, that is 1, minus numerator x into derivative of denominator, so it is 2x square, so minus 2x square, so it is simply minus x square plus y square. Okay. Okay, so this is our first entry, this minus partial derivative of this with respect to y. Okay. So simply you can see that. Yeah, sorry, I'm finding partial derivative of this. Okay, so consider this 2 by 2 submatrix. Okay, sorry. So this is equal to I had into. So this is 0 minus derivative of this quantity with respect to z, it is 0 minus z hat. Now I am differentiating this with respect to x, it is 0, and this with respect to z again 0, and plus k hat into. So derivative of this with respect to x minus derivative of this with respect to y. So first thing is minus x square plus y square upon x square plus y square bracket square minus. Okay, so is minus sign here. Okay, so it is, this will be plus, and we get minus y square plus x square upon x square plus y square bracket square. So we can see that it is 0. Okay, so curve is 0. Next thing is we are asked to show that divergence is 0. Okay? So divergence of f is del dot f, and that is partial derivative with respect to x of first component of it. It is minus y upon x square plus y square plus partial derivative with respect to y of second component x upon x square plus y square and third quantity 0. Okay. So this we just have same, it is nothing but this quantity. Okay. So clearly it is 0. Let us solve example. Find Jacobian curl and divergence. So our f is given by x square plus yz, I hat, then plus y square plus xz, j hat, and last term z square plus xy, k hat. Okay. So let us solve this solution. First thing is Jacobian. So it is given by, it is denoted by capital DF. So first row is partial derivatives of this first component P with respect to x, y, and z. So with respect to x, the partial derivatives are 2x. The partial derivative is 2x. Then with respect to y, it is z, and with respect to z, the derivative is y. Similarly, second row is partial derivatives of this function q. So with respect to x, it is z. With respect to y, it is 2y. And with respect to z, it is x. Similarly, third row, derivatives of this quantity. With respect to x, it is x. With respect to x, it is y. With respect to y, it is x. And with respect to z, it is 2z. So this is our Jacobian matrix. Next is curl and divergence. Okay. So let us find curl. Curl f equal to del cross f, and it is matrix of a determinant whose first row is I hat, j hat, k hat. Second row is partial operators. Third row is components of f, x square plus yz. Second is y square plus xz. And third is z square plus x square. And it is I hat into this with respect to x, it is z, minus this with respect to y, it is z, plus j hat, it should be minus j hat, into derivative of this with respect to x, it is y, minus derivative of this with respect to z, it is y, plus k hat, derivative of this with respect to x, it is z, minus this with respect to y, it is also z. So it is clear that curl is 0 here. Okay. Next thing is divergence. Divergence is simply del dot f that is equal to partial derivative of first term with respect to x plus partial derivative of this with respect to y, and then plus partial derivative of this third component with respect to z. These are appearing on the diagonal of Jacobian matrix. So these are required things. So we just add these things. So 2 times x plus y plus z. Okay. So this is required thing. Okay. Now next example is, let phi of xy z be xy plus y sine of z. Okay, this be a scalar. Find gradient of this vector field. Solution: grad phi equal to del phi, and that is equal to partial derivative of phi with respect to x I hat plus with respect to y j hat, and plus with respect to z k hat. That is equal to, here we already found this with respect to x, with respect to y, with respect to z. So all these are diagonal elements. So 2 x I hat plus y z hat plus z hat. Okay. So this is the required gradient. Okay. Next time we see some more properties of these operators. Thank you.